Good morning. Hopefully everyone can hear me okay. My name is Laura Brenneman. Thank you, Ramesh, for the introduction. I'm a scientist up the street at SAO, and I work in the high energy division, so this will be an observation-oriented talk. But I wanted to tell you guys a little bit about the work that I do with X-ray observations of AGN looking to measure black hole spin, mainly using X-ray reflection spectroscopy. So I'll go into a little bit about what we know so far about AGN structure, knowing that this is a bit of a varied audience. And then I'll focus in on the topic of black hole spin itself, primarily the fact that we think that spin could be the link between accretion in these galaxies and ejection in the form of the so-called feedback that we see possibly regulating star formation. I'll also talk about the contents of the X-ray spectroscopist toolkit in terms of how we use observations to get at the information so close to the black hole event horizon. And then I'll discuss the results so far on supermassive black hole spin constraints and their biases and implications, as well as a little bit on systematic error. And then I'll talk at the end a little bit about summary and future directions. So we're going to hear a lot about this conference, I imagine, and I bet you guys already have, about how it is that black holes, which are so small in comparison to the size of the overall galaxies in which they reside, how it is that they have such an intimate relation to their host galaxy. And in the plot on the right, you see what we call the M-sigma relation, which is a plot showing stellar velocity dispersion versus black hole mass. And it appears that there's a very tight correlation there over many orders of magnitude in black hole mass. So the question is, the stars in these galaxies are way outside the gravitational sphere of influence of these black holes. How is it that there exists this tight correlation if it isn't gravity that's driving this process alone? And the answer, we think, has come in a bit of an indirect sense in the form of some observations of galaxies plotted against the theoretical cold dark matter halo expectation of what we would see here. And it looks like we have a deficit here, both on the high mass end and on the low mass end, in terms of the number of stars, the brightness of stars being a proxy for the number of stars that we see. And we think that these feedback processes, largely driven by the black hole, can be responsible. Especially here at the high mass end, we see that when you have AGN present in these galaxies, it seems that there is a significant deviation from what we expect from the cold dark matter halo theory. And the way we think this happens, just to give you a big picture, this is a beautiful example from the Illustra simulation here, is through this process known as feedback. So you have an AGN driving activity at the core of these large galaxies and galaxy clusters. And it can drive warm gas out into the ambient medium of the galaxies and the clusters. That warm gas, unlike cold gas, doesn't preferentially collapse gravitationally. And thus, you have a warmer ambient medium which is less prone to forming stars. So on the left, you see a simulation that doesn't include any form of cooling, star formation, or feedback from the AGN. On the right, you see a simulation that does. And you'll notice that there's a lot more pink, if you can see with the contrast on the screen here on the right, when you include those effects of winds and feedback and jets from AGN than there is in the case where you have merely an adiabatic simulation. So in terms of how we understand this, we think we have an idea about the big picture, that feedback regulates star formation in these galaxies and can drive galaxy formation and evolution. But it's the particulars that we lack an understanding of. And in order to get that understanding, we have to zoom in much closer to the black hole and its event horizon in order to try and figure out the causal connections between how the black hole drives these outflows and how these outflows might connect on a larger scale to the host galaxy. So when we do zoom in, we notice that X-rays become a very handy diagnostic to use because X-rays allow us to probe material as close as we possibly can to the event horizon before it plunges into the black hole. And it also allows us to probe things like the origin of jets and the origin of outflowing winds that are driven off the accretion disk either by thermal or radiative processes, maybe even magnetic processes in some cases. So the big things with AGN structure are you have, of course, the black hole at the center, which does no emitting. Then you have the accretion disk, which is primarily an engine for reflection from what we call the corona. The corona, of course, is this sea of relativistic electrons that exist in some as yet unknown geometry around the black hole itself. And from this, we see what's known as the X-ray continuum emission. So thermal emission from the accretion disk interacts with these electrons, Compton scatters off of them, and then comes to our X-ray telescopes in the form of a power law-shaped continuum in the X-ray band. Some of that emission, however, scattered from that corona, reflects back down onto the surface of the disk, forming some very interesting features that modify that continuum emission. And then we may or may not have a jet in some AGN. Many do, many don't. And then we also have what's known as these outflowing winds, which create absorption lines in the X-ray spectrum. So to give you an idea of what this looks like, here is actual data from the Suzaku X-ray telescope in this case of one particular AGN that we've studied frequently for black hole spin measurements, MCG minus 63015. This is with that continuum power law modeled out. So we've taken out the power law continuum to show you the residual features that are left. This huge trough that you see is called the warm absorber, and that's evidence of these X-ray outflowing winds. Then you see this spike up here in the iron K alpha band. This is from a combination of both reflection from distant material, far from the black hole, as well as more proximal reflection, closer to the event horizon. That proximal reflection creates this red wing that I'll touch on in a minute. And then actually at higher energies, you can see further evidence for more highly ionized absorption from these X-ray outflows that you see. And finally, when you get up to higher energies that Suzaku and now we have NuSTAR can really probe, you see this sort of rollover known as the Compton hump. And that's shaped by both Compton processes on the high end and by this X-ray absorption here on the low end. There's an iron K edge that shapes that hump. So these are the features that we typically look at when we're analyzing X-ray spectra and looking for evidence of black hole spin and outflows. Particularly this area with the iron line and Compton hump is what I'll refer to as the reflection spectrum. Now, how does this all tie into outflows? So back in 2007, we had an interesting paper published by Sikora et al. That showed that there were effectively what looked like kind of a bimodal distribution of radio power versus Eddington fraction here being a proxy for mass accretion. And what we saw was that there were really two divisions here. And it was thought that in addition to how much mass you accrete, being able to drive how much outflow you can produce, black hole spin also should play a role. We know that from things like the Blandford-Nyack effect and the Blandford pain mechanism, but here we seem to see evidence for something in addition to how much mass you're creating, playing a significant role in driving jet production here, where radio loudness is sort of a proxy for jets. So black hole spin could be the hidden link there. Certainly magnetic fields also play a role, but that's one thing to keep in mind. Also, one of the things that we're very interested in studying black hole spin for is that it's really a good indicator of the overall gas accretion history versus the merger history of black holes. So are they growing primarily by merging with other black holes, or are they growing primarily by accreting lots of gas from their surroundings? That's another interesting question that we hope to probe with black hole spin measurements. The way we actually go about measuring spin is by playing off of a very nice monotonic relationship between the spin of the black hole and the radius, what we call the marginally stable orbit in the accretion disk. This relation is set by Einstein's theory of general relativity, and as you can see, whereas the event horizon kind of varies like this with spin, where spin can go either negative to a normalized value of 1 or positive to a normalized value of 1. In this case, positive spins are the black hole and the accretion disk spinning in the same direction. Negative spins mean that the black hole and accretion disk are spinning in opposite directions, which is unusual, but theoretically possible. In any case, the great thing about the radius of marginal stability is that there is this nice monotonic relationship here, so that if you can measure RMS, you have a proxy for the spin of the black hole. And the way this actually works in the accretion disk and in observations in terms of how we make these measurements are we look again at this iron K alpha line, that spike that I showed you on one of the prior plots. And if you take all the emission from different annuli in the disk and you combine them, what you expect isn't a typical emission line profile like you might see from iron gas in a laboratory. What you see is actually something that's quite a bit broadened and skewed by Doppler and relativistic effects. So to give you an example of how this works, if we look far out in the disk, say at 400 gravitational radii, we see Doppler shifting that's primarily shaping this line. As we move in, and I don't know if you can pick up the blue line here with the contrast on the screen, you see that this line starts to become wider and asymmetric. Special relativity is beginning to play a role. Moving in farther, you see that that asymmetry becomes more pronounced, and especially beaming, preferentially on the blue wing of that line, and sort of de-beaming on the red wing of that line, become more pronounced. Moving in farther, the effect increases. For a non-spinning black hole, the radius of marginal stability is at 6 gravitational radii. That's set by GR, so you can't go any further in than that. And in that case, obviously, you see a very broadened and reddened profile. The whole centroid of that line has been dragged down to lower energies by relativistic effects. So when you combine the radiation from all these rings in the disk, what you see is the black line here. So it's kind of the summed emission from all of these annuli. And you can see that it's highly broadened and skewed. And it turns out the red wing, the location of the red wing, the redmost part of that line, is a great proxy for that radius of marginal stability for the black hole spin, in other words. So when you look at prograde versus retrograde cases, or in the case of a non-spinning black hole, you expect a different shape for this reflection spectrum. So to first order, at least, for a retrograde rotation, you have a plunging radius instead of being 6 gravitational radii. It's been pushed all the way out to 9 gravitational radii. So the line gets narrower, and the reflection spectrum doesn't change too much at high energies, but there are subtle changes there as well. As you move in with your radius of marginal stability for a non-spinning case, the line gets a bit broader. And as you move further in still, for a maximally rotating prograde black hole, that radius of marginal stability is practically sitting on the event horizon. And in that case, more of your emission is coming from deeper within the potential well of the black hole, so you get more broadened and skewed emission. Now, the complication, observationally speaking, is when you're looking at these reflection spectra, how do you deconvolve all the absorption features from the gas along your line of sight to the black hole? Remember, these black holes sit in the middle of galaxies, and galaxies have gas, and they have dust, and they have all sorts of junk in the way. Now, if you ask my colleagues in the optical and infrared division, they might not consider this junk, but one man's trash is another man's treasure, so I try and see through this. And the problem is that this absorption can do a devilishly good job at mimicking reflection spectra in some cases. So if you can see here, this absorption can take a chunk out of the spectrum and create curvature up here at the high energy end and the iron line end. And it mimics, very closely at least, this feature over here that gets produced from the reflection off the disk. So one of the things that we've come to realize that we really need, and we've realized this since the launch of NuSTAR, is we really need this high energy information up here, because this is what really enables us to help tell the difference between absorption models that can create these spectral shapes and reflection models that can create very similar spectral shapes. They deviate on the high energy end. So broadband X-ray spectra have turned out to be really necessary for black hole spin measurements. Let me illustrate this for you. This is an AGN known as NGC 1365, and these are 4 observations that are collected and been plotted here with XMM and NuSTAR simultaneously several years ago. It turns out that when you only plot the XMM Newton data, which is shown here on the soft end in green, and you fit it with reflection or absorption models, they fit equally well if you go up to about 10 keV, which is where XMM Newton starts to lose effective area rapidly. However, when you plot the NuSTAR data, here shown in blue, on top, it turns out that it very closely resembles this black line showing the reflection spectrum, and it does not resemble this red line showing the extension of the absorption model out to higher energies. This hasn't even been fit to the data, let me be clear. This is just data and models laid on top of each other. And as you can see, even without doing any spectral fitting, the reflection model fits much better in this case. This is an object that absolutely does have complicated absorption structures in its inner nucleus. There are clouds rotating into and out of the line of sight. There are outflowing winds. This is a very rich source, spectrally speaking. However, for every source that's actively accreting, every source that has an appreciable accretion rate, we expect that you're going to see an inner disk extending down to at or near the radius of marginal stability. And we expect that you're going to see these relativistic reflection features from right close to the event horizon. The issue is whether there's enough absorbing gas in the way to block our view of that reflection. So one of the great challenges in X-ray spectroscopy is, can we separate, can we break those modeling degeneracies and figure out, truly isolate where the reflection is and measure the black hole spin from that. This source, when it was observed in this campaign, each of these observations was taken several months apart for about 120 kiloseconds. And you can see that this source varied hugely over that time. Hugely. This is less than a year's worth of data. And it varied in column density of the absorbing gas by 2 orders of magnitude, a factor of 100 over a few months. Interestingly, when you take out the absorption, when you take out the continuum from that power law shape that we see from the corona, if you look at the reflection spectrum in each one of these cases, it is almost identical. This is great. This is proof of concept that we actually can see these features that we expect and that they're staying roughly the same. When you're talking about black hole spin measurements, black hole spin probably changes on roughly the amount of time it takes an object to accrete a significant portion of its own mass. So for a supermassive black hole that weighs millions or billions of times the mass of our sun, this is going to take a very long time for spin to change. So every snapshot we get in X-rays from one of our orbiting telescopes right now is going to give us the same spin. It hasn't changed. So we should get the exact same spin measurement from each one of these 4 observations if the theory is correct and if we're really seeing relativistic reflection. Comfortingly, we do. So here on the right-hand side, I'm plotting the spin, the chi-square, the goodness of fit for different spins as you probe the parameter space. And as you can see, each one of these epochs gets a spin measurement very, very close to its maximal value. We can also do this for radio loud sources. So the source I just showed you, NGC 1365, is radio quiet. Here, we see an example, 3C120, of a radio loud source. This has a very prominent jet. And jets make our lives difficult because when they emit in X-rays, they can confuse the spectrum. So it makes it very difficult to disentangle jet emission from reflection and from the continuum from the corona as well. However, interestingly, what we're seeing is that when VLBI observations are taken simultaneous with UV and with X-ray data, we see that there are dips in the X-ray light curve and even parts of the UV light curve that seem to correspond with the emission of clumps or knots in these radio jets. This is very suggestive. And it turns out that when you do planned campaigns, as has been done a few times with 3C120, and you take observations in X-rays either before or after a jet ejection event, you notice different measurements of the inner radius of that disk. So it turns out that for this black hole, if you take an observation right before a jet ejection event, you get a very, very low inner radius of the disk, something very close to the marginally stable orbit. If you take an observation right after a jet ejection event, it looks like the disk has actually moved out. The inner edge of that disk has been pushed out. So one idea that people have had to explain this is perhaps there's a cyclical effect where there's some sort of instability that forms in the inner part of the disk and gets ejected when you have these radio knots, these blobs of emission ejected in the jet that we see. And then through another mechanism, the disk somehow refills itself in between ejections. We don't know how this happens. This is what seems to be happening based on our observations, but we still need theory to be able to explain this phenomenon. We've had a hint that perhaps there's a close link, observationally, between jets and spin in microquasars. And Ramesh has been instrumental in this work. As you can see, there's a plot of several different galactic black hole binaries that have had their jet power measured, as well as the ISCO here, the ISCO radius. And you can see that there is apparently a connection. It's still early days. We don't have many data points on this plot, but it's tantalizing evidence that perhaps we really are seeing some sort of clear connection here, either by the Blanford-Nyack effect or some other mechanism quite similar between the black hole spin and radio powering jets. So the question is, does this connection also seem to connect to higher masses in AGN? We don't know the answer yet. Like I said, black hole spin can also be a proxy for how a galaxy and a black hole has grown over time. Is it primarily through mergers or is it primarily through accretion? And it turns out that numerical simulations predict very different answers depending on which of those growth mechanisms takes place. Long story short, if you grow primarily through mergers, you seem to have a very broad distribution of spins at the end. If you grow primarily through chaotic accretion, as in an episodic accretion from all different angles, you wind up with, by and large, fairly low spins at the end. Whereas if you grow by prolonged, prograde accretion, it's like spinning a basketball on your finger and just keeping pushing it in the same direction. You eventually spin up and up and up until you have a near maximal set of black hole spins at the end. Here's how we've done so far. In the literature, there are now 31 supermassive black holes with their spins measured via this reflection technique I discussed. It turns out that we are heavily weighted towards high spin. Also, this is an interesting study, there was a sample of 27 lensed quasars at much higher redshift taken by Don Walton et al. In 2015, and it turns out that when you add up all their spectra, the signal-to-noise wasn't such that you could do them individually, but when you sum all their spectra, these 27 sources at higher redshift, you get an aggregate spin of about 0.7. So, interesting evidence that this may bear fruit over high redshift as well. So bottom line, we're seeing lots of rapid spinners, but none that are consistent with non-spinning black holes so far. Now, early days, a sample of 31 is not exactly what you would call a statistical distribution at this point, but it is interesting enough that we can start probing some correlations. Of course, there may be selection biases. We're picking low-hanging fruit, and we're looking at very bright systems. It's expected that the very bright systems might be biased toward higher black hole spins because you have more energy coming from these things due to the loss of gravitational potential. But in any case, If you were to plot the spin distribution against mass, maybe if you squint a little bit, you can start kind of seeing an inverse relation here. Again, early days, and of course we only have this one data point at, very high masses, but again, early days, keep it in mind, back pocket, this could bear fruit later. Interestingly, when you plot the spin versus the Eddington ratio estimated of these sources, it turns out that this is approximately constant. So right now, it doesn't look like we're really seeing a robust relation between those two things, which is interesting in and of itself. But again, selection biases could come into play. By selection biases, in addition to the fact that we're picking the brightest objects, we also have systematic uncertainties that are coming into play. And if anyone wants to talk about these, I'm more than happy to do it afterwards. I don't have time to go into all of them. But just to list a few, we assume that the inner portion of the disk goes down to about the ISCO when we make spin measurements. We have to in order to play out that monotonic relationship. So there are differences that could occur if you have emission coming from within the ISCO. We don't think it would be significant, but it could induce variations on about the 20% level to your measured spins. We also think that if you truncate the disk somehow outside the ISCO, then in that case the spin that you measure would be a lower limit. We also make a lot of simplifying assumptions about the structure of the disk itself. We assume it has a constant density, a constant ionization. We assume it's geometrically razor thin. All of these things are almost certainly not true, but they're things that we have to assume right now in order to build models that work and that fit to the data. And we also assume that the black hole disk is aligned with its spin axis, which may or may not be true. Bardian-Pedersen effect could certainly play a role in creating disk warps. We also assume that the corona is compact, but we know nothing right now about its geometry. It could have a radial or vertical extent. It could be the basic jet. There could be an outflow associated with it. All of these things fold in to give us some systematic uncertainties. However, for the high spins that we're measuring, by and large, these systematic uncertainties are beaten down. They become more important for lower spins. So I'll just leave you with a few thoughts. First of all, we need broadband X-ray spectra in order to make black hole spin measurements. We have a sample of about 31 of these measurements so far in local AGN, though care must be taken in model fitting to avoid degeneracy, especially with absorption. We're not seeing any non-spinning black holes at the moment, though stay tuned. We do need a larger sample size, of course. 31 is not enough, as I said, and we hope that with future instrumentation, we'll be able to probe farther out in the universe and also to fainter black holes in our local universe and start getting a more representative sample of spins in certain types of black hole hosts, and especially in radio loud sources. So thank you very much, and I'm happy to take questions.
I was just wondering what you would, if you looked at what you would see if the spin was greater than 1, and if that plot that you showed can be viewed as a strong test of the Kerr bound.
Which plot?
That one.
So we haven't actually got models right now that are regularly used that probe spins greater than 1. We're assuming there are no naked singularities out there in the universe. We're assuming the GR is correct. There are people who are working on models, Tim Johansson is one of them, that work, that build off of perturbations that might exist in GR that can probe these perturbations. Those models are really more effective in looking at things like curvature near the event horizon and are therefore a bit more applicable to things like galactic black holes that have higher curvature than AGN because of their lower mass. So that's one area that I know Tim is exploring, but that we're not probing right now with this study.
Yeah, so actually, Andy, maybe I will comment.
It seems like a very impressive thing that curve predicted 50 years ago that curve ends at 1. And I'm wondering whether you built that in somehow to your normalization, or whether we're seeing this.
This is built into the models. The models do not go higher than +1, and they do not go lower than -1 right now.
So I think
But it's not hard to write the overspinning metric and check the redshift, right?
You could do it. I'm not sure that the data would be able to distinguish between something slightly over 1 and slightly under 1 right now, so I'm not sure how useful that would be.
Yeah, Alison.
But because they use the ISCO, will you have an ISCO if you have an overspinning? I mean, there is something that they use in. Well, no.
We're assuming that it's all coming from right outside the ISCO, as a matter of fact, either at or outside. We're
but
assuming
there
that none
is,
is coming
but
from
there
within.
is an ISCO in your. You assume that it's important that there is the ISCO, no?
We assume that there is an ISCO, and I think Ramesh can also probably tell you about studies that have been done with galactic black hole binaries, and again, showing the variation of this ISCO. It's got a good solid radius over different accretion rates for a long time. Occasionally it has been shown to vary when there are jet ejection events, but for the most part when you have a non-jetted source, that ISCO seems to be a very hard boundary over many different accretion rates and observations that have been taken. So we have every observational piece of evidence to believe that there is an ISCO at this point. There's nothing showing us otherwise.
Okay. Avi first? Okay, go ahead, Chuck, it's all right. It's all right, we'll give you the...
I'm quite interested in the possibility of a retrograde spin. So do you have any evidence of any sources anywhere being retrograde, and how many would you expect given mergers and merger rates of retrograde spins?
That is a great question, and I wish I had a better answer for you. Obviously, our distribution doesn't show any in the AGN right now. There are some galactic black holes that are consistent with possible retrograde spin, as in they have lower error bars that seem to go into retrograde values. Whether that actually means they're retrograde or whether we need to beat down uncertainties is a different question. The problem with spins that are low is that the nature of the spin parameter space makes it a lot easier to constrain higher spins than it is to constrain lower spins. So, for example, a black hole spin of 0.99 is a whole lot different than a black hole spin of 0.9, whereas a black hole spin of 0.5 kind of looks about the same in many ways as a black hole spin of 0.1. So you get, by nature, much larger error bars on lower spin values than you do on higher spin values. That makes it challenging, number one. Is it theoretically possible? Yes. There are certainly issues where you could have mergers, for example, that could produce a retrograde spin. Now, the Bardeen-Pedersen effect would tend to sort of, if there's any gas involved in these mergers, it would tend to create a drag that would eventually align the spins, you would think. So it would have to be a bit of a special case, but you can imagine it happening and living that way for an appreciable length of time. Have we definitively seen one of these? No, we have not definitively seen one of these in an AGN so far.
An important point to keep in mind is that this is not a fair sample of all black holes. These are black holes that are accreting at the time that we are observing them, and therefore they may be biased towards
Absolutely.
Spins of one. And
Absolutely.
the real census of black holes would come from LISA in a decade or so, when we could see, the entire population merging, and during the process of merging, we can tell perhaps what the spin is of the two black holes that are coming together.
I think that's a great point, and I think that gravitational radiation is opening a whole new window onto this science. Of course, there are going to be biases in the distribution of spins we get there, too, because we're looking at merging systems.
No, but we can tell the spins of the two components before they merge, actually.
True, but then we're still looking at systems that are quite close together. So when we're talking about isolated black holes, those are the ones, the isolated ones that aren't accreting a lot are the ones that we have a really hard time going after in terms of measuring their spin. And they're probably a huge fraction of what's out there in the universe. So any spin measurements that we make, either with gravitational radiation or with electromagnetic radiation at the moment, are going to have inherent biases built in based on what we're able to observe. That's a really important thing to keep in mind.
So, Laura, I had a question. So, in the early days, when the first famous source, MCG 63015, its spin was measured. Its spin was close to 1.
Yes.
And it's a very radio quiet object. So in terms of this dichotomy you mentioned, in terms of jet power, this guy had a high spin but essentially no jet.
True.
Right, which was a worry because, as you said, the natural assumption is that this radio power should be correlated with spin. So now that you have a sample of 31, if you took those guys and put them on that plot, do they show any correlation with jet power?
Well, the problem is this is a sample that is almost exclusively radio quiet. That's an excellent question, but as I said, the problem with getting radio loud sources is that when they also have X-ray, or rather when they have jet emission in the X-rays, that contaminates what we want to see. It prevents us from cleanly isolating the reflection spectrum as much as we'd like, because that jet emission, when it's in the X-ray band too, kind of creates a little bit of a kink in the spectrum that can make it very difficult to separate the continuum from the reflection, and the reflection is what we need to study spin. So that's a great question, and we hope that if we are persistent in getting campaigns like the one that we saw on 3C120 for other radio loud sources, eventually that they will bear fruit. But It's tricky because those are the exact sources that we really want to be measuring the spins for, but this method is complicated. So there are some people who are actually trying to use alternative methods to measure spin in sources such as those. I didn't have time to get into those methods, but we'll see if those hold up over time as well.
Very quickly, Andy, we need to move on.
I just wanted to make a comment. I just want to make a comment that this is a graph of what a condensed matter theorist would call an attractive fixed point, where you have a phase space of possibilities, and things are attracted towards one point, and that's what that just saying how it would be referred to in other language.
Interesting point. Yeah, it's certainly catches the eye when you look at it. I mean, it certainly seems to look back at those numerical simulations and say, wow, maybe we're seeing evidence for a lot of accretion growth as opposed to a lot of merger growth or a lot of chaotic growth. Again, sample of 31, it's hard to draw any definitive conclusions yet, but it is tantalizing for the future. And again, I think that we really need to get a much less biased population of black hole spins in order to start really coming at that question. So we'll see what the future holds.
Great. Thank you, Laura.
Thank you.